The paper presents a fermionic description of flagged k-theoretic symmetric polynomials, specifically flagged skew-Grothendieck polynomials. These polynomials are a k-theoretic counterpart of flagged skew-Schur polynomials. The proof relies on the Jacobi-Trudi type formula established by Matsumura. This result generalizes the author's previous works on fermionic descriptions of skew-Grothendieck polynomials and multi-Schur functions. Grothendieck polynomials, introduced by Lescaut and Schutzenberger, represent the structure sheaf of a Schubert variety and the K-theory of the flag variety. Each Schubert variety is naturally associated with a permutation, making Grothendieck polynomials indexed by permutations. Flagged Grothendieck polynomials, a K-theoretic analog of flagged Schur polynomials, possess interesting combinatorial and algebraic properties. A permutation W is called vexillary if the family of inversion sets, E, W, forms a chain by inclusion. For a vexillary permutation W, a partition lambda, W, is associated by arranging the cardinalities of inversion sets in decreasing order. A flagging of W is the sequence obtained by arranging min E, W, 1 in increasing order. The flagged Grothendieck polynomial GW, X, is often written as G lambda, F, X, where lambda equals lambda, W, and F is the flagging of W. Matsumura generalized flagged Grothendieck polynomials for skew shapes lambda, micro with a flagging F per gram, where F equals F1, Fr, and G equals G1, Gr, are sequences of natural numbers. He proved that a flagged skew-Grothendieck polynomial admits a Jacobi-Trudi type formula. The determinant formula is expressed as equation 2, which involves the generating function g, p, q, n, x, defined in equation 1. The paper's main contribution is the fermionic description of flagged skew-Grothendieck polynomials, which relies on the Jacobi-Trudi type formula established by Matsumura. This result has implications for the study of k-theoretic symmetric polynomials and their connections to algebraic combinatorics. The authors investigate flagged skew-Grothendieck polynomials, adopting a modified definition given by equation 3, which facilitates algebraic calculations. This definition yields the polynomial G lambda, micro, F per gram, X, in equation 4, differing from the standard Grothendieck polynomial G lambda, micro, F per gram, X, but coinciding with it under certain conditions. Specifically, this occurs when phi plus lambda I is greater than or equal to Gj plus micro Jj whenever phi less than Gj1. The authors seek to provide a novel algebraic description of G lambda, micro, F per gram, X, by leveraging concepts from vertex algebras, including fermion-Fock spaces, vertex operators, and vacuum expectation values. They generalize the fermionic description of skew-Grothendieck polynomials presented in previous work to flagged Grothendieck polynomials, culminating in the main theorem, a fermionic description of the flagged Grothendieck polynomial. The descriptions, given by equations 13 and 19, are novel and not found in previous work on multi-Schur functions, suggesting that there is still room for generalization of fermionic descriptions of k-theoretic polynomials. In the preliminaries section, the authors introduce the fermion-Fock space, generated by the free fermions psi n and psi asterisk operator n, with anti-commutation relations. The Fock space F is defined as the left A module generated by the vacuum vector 0, and the dual Fock space F asterisk operator is defined as the right A module generated by the dual vacuum vector open angle bracket 0. The authors also introduce the anti-algebra involution asterisk operator and the vacuum expectation value, a unique CBI-linear map from F asterisk operator circled times kf to k. The discussion focuses on flagged k-theoretic symmetric polynomials, particularly the expectation value and Wick's theorem. It introduces normal ordering for expressions involving creation and annihilation operators. Vertex operators and their commutation relations with fermion fields are also presented. The expectation value is defined as in bracketly T0, x, 0, in bracketry ht, often abbreviated as in bracketly Tx, in bracketry ht. Wick's theorem states that for sets of integers, M1, MR, and N1, NR, the expression, in bracketly, T psi M1 psi Mr psi asterisk operator NR psi asterisk operator N1, in bracketry, HT equals the determinant of, in bracketly, T psi Mi psi asterisk operator Nj, in bracketry, HT. Normal ordering is defined to move annihilation operators to the right, multiplying by 1 for each move, ensuring correct ordering for commutation relations. The vertex operators are introduced, including their commutation relations with fermion fields, highlighting their importance in quantum field theory. The flagged skew Grothendieck polynomial is presented in a fermionic framework, where the notation x, f per gram, denotes a sequence of functions for brevity. By combining expressions, 79, equation 11, is derived, revealing that the exponential of the Hamiltonian h, x, f per gram, acts as a generating function for the flagged skew Grothendieck polynomial g, f per gram, when applied to the wave function psi, z. This equation has significant implications for understanding the role of the flagged skew Grothendieck polynomial in quantum many-body systems and their algebraic properties. Furthermore, equation 12 demonstrates the action of the dual Hamiltonian h asterisk operator, x, on the dual wave function psi asterisk operator, w, providing a crucial insight into the algebraic structure of these systems. These equations collectively underscore the importance of the flagged skew Grothendieck polynomial in the context of quantum many-body systems, highlighting its potential as a powerful tool for exploring their properties and behavior. The research paper explores the fermionic description of skew-flagged Grothendieck polynomials, defined by a determinantal formula. The main theorem, Theorem 3.2, expresses these polynomials in terms of an expectation value involving noncommutative elements and annihilation operators. This expression is derived through transformations leveraging the Hamiltonian and annihilation operators properties. The paper also introduces flagged skew Grothendieck polynomials, detailing their structure and properties. The application of Wick's theorem to a specific determinant is crucial for evaluating the expectation value of a particular expression. The authors introduce functions I and bj to simplify the determinant, defined in terms of summations involving the parameters psi, and beta. The paper derives expressions for I and bj, highlighting their properties and connections to previous equations. The key takeaway is the transformation of the original expression into a more manageable form using these functions, ultimately facilitating the computation of the expectation value. The authors derive an expression for the flagged k-theoretic symmetric polynomial using the bracket notation, expanding the rational function f, z, w, in the field C, x1, x2, w1, z, beta. This expansion, given by equation 10, involves products of terms of the form 1 plus beta xk and 1 beta zk over indices k. To extract the coefficient of z lambda ew micro jj in f, z, w, the authors employ a complex line integral, evaluating f, z, t1, as a sum of products and computing the residue of the differential form at t equals z. The result is expressed in equation 18, where the coefficient of z lambda ew micro jj is a sum over S of terms involving the generalized flag g, phi, gj, and binomial coefficients. This result is then used to compute the coefficient of z lambda 11.1 z lambda rrrw micro 11.1 w micro rrr in the determinant 16, which is expressed as a determinant of sums over S of terms involving the generalized flag g, phi, gj, and binomial coefficients. Comparing this result to equation 4 leads to the conclusion of the theorem. This page presents a technical derivation of an expression for flagged k-theoretic symmetric polynomials using complex analysis and algebraic manipulations. The reduction of the skew Grothendieck polynomial to the flagged Grothendieck polynomial is a crucial step in understanding the algebraic combinatorics of flag varieties. A novel expression for the skew Grothendieck polynomial is derived by specifying particular values for the parameters and applying the main theorem. This result is significant, as it provides a unique perspective on the polynomial, diverging from previous fermionic presentations. The skew-Grothendieck polynomial is a vital component in the study of flagged Grothendieck polynomials, and its reduction offers valuable insights into the structure of flag varieties. By leveraging the main theorem, the derived expression for the skew-Grothendieck polynomial enables the exploration of new properties and relationships within these algebraic objects. This novel contribution is particularly noteworthy, as it deviates from previous approaches that relied on fermionic presentations. The distinctiveness of this finding lies in its ability to provide a fresh perspective on the algebraic combinatorics of flag varieties, thereby expanding our understanding of these complex mathematical structures. The significance of this result lies in its potential to unlock new avenues of research, enabling the investigation of flagged Grothendieck polynomials in unprecedented ways. Furthermore, the derived expression for the skew-Grothendieck polynomial may have far-reaching implications for the study of algebraic combinatorics, shedding light on the intricate relationships between flag varieties and their associated polynomials.